going over modules 14 and 15 today, which are the last two modules in this course for the semester, which is kind of wild. Like, we're basically done after these videos. That's kind of insane. But yeah, y'all made it through. Woohoo. So what we're going to be going over first is oxidation numbers, and this is going to be a fairly shortish video because it should be more of a review. I just didn't want to put it too much with the other one because then the video would get way too long, and I hate really long videos explaining things because I lose track of things. So yeah. But okay, if you guys recall, your oxidation numbers, they aren't the charge of your compound. They add up to it, but they're not the total charge. Like, your things aren't just -1. Essentially what an oxidation number is, it's that every atom has a charge if it were to be sharing the electrons with the most electronegative one. So I know that sounds weird, but it's essentially just the most electronegative one gets all the electrons and the other one has to match up to it. So like if something's really negative, the other thing has to be really positive because it gave its electrons to the other thing. So yeah. So when we're solving for oxidation numbers, there's some rules to it, which number one is that any atom in its most stable / elemental form, so any atom in its most stable / elemental state, oh my god, why are my T's not crossing? Okay, has an oxidation number of 0. So what this means by elemental state or more stable state, it's kind of your diatomic elements like H2, O2, Cl2, anything like that. It has an oxidation number of 0. Just because they're really stable, they're not going to be sharing electrons with anybody else but themselves. So 0. And then your second rule would be that group 1 and 2 elements have an oxidation number of +1 and +2 respectively. As in, if you're in group 1, you have a +1 charge, and if you're in group 2, you have a +2 charge. So for instance, sodium, which is a group 1 element, would have an oxidation number of +1, and calcium, which is a group 2 element, would have an oxidation number of +2. So then your third rule would be that the hydrogen ion, which is H+, has an oxidation number of +1. So yeah, no example for this one because it's just the hydrogen ion. And then, hold up, I need to make more room, sorry. A fourth rule would be that your oxygen atoms, oxygen in any compound has an oxidation number, of -2, and this is essentially for every oxygen in it. But take for instance, if I were to do H2O, the oxygen would equal -2 as its oxidation number. Ooh, that was a lot of OX's in that sentence. But yeah, so in a compound, for instance, and just it mixed with something that isn't another oxygen, -2. So then a fifth rule would be that halogens in compounds have an oxidation number of -1. And that's the same thing as I said before. If it's with something mixed that it isn't within itself, then it'll have its oxidation number of -1 usually per every halogen. So in HF, its oxidation number of fluorine, I'm pretty sure that's how you spell that, is -1. And also, like I said before, oxidation numbers, well, okay, that's the sixth rule, essentially, that oxidation numbers add up to the total charge. So an example of this, an easy one, would be HCl, where the total charge, so I'm going to write it over here, total charge is 0, right? Because it doesn't have a minus or a plus next to it, it's 0. These things cancel each other out. You have a positive and a negative. So then, per our rules, a hydrogen ion has an oxidation number of +1, and a halogen in a compound has an oxidation number of -1. So therefore, if we add 1 plus a -1, we get 0. They cancel each other out. And also, like I said, well, no, like, sorry. And so the oxidation numbers of these things, it would just be hydrogen has an oxidation number of +1, and chlorine has an oxidation number of -1. So then another example where it's not as easy to figure it out would be carbonate, where the formula is CO3 2-. So I'm going to write over here that our total charge is -2. So then we know that our oxygen in a compound has a charge of -2, right? So oxygen equals -2. And since there's 3 of them in this one, we would do -2 times 3, because it's a -2 charge per each oxygen, which means we have a -6 oxidation for our oxygens. So we have to equal it to our total charge, and we don't have any rules for carbon yet. I'm going to change the color just so that we can see this. But yeah, we don't have any rules for carbon because it's not in group 1, it's not in group 2, it's not a halogen, it's not an oxygen, and it's not a hydrogen. So we're going to have to add it up to the total charge to figure out what the charge of our carbon would be. So our total charge is -2, which is equal to the -6 from our oxygen plus whatever carbon is. I should have done that in blue, considering that that's what I was doing. So yeah, there we go, our carbon. So then we're going to do just algebra plus 6, or basic arithmetic. I don't think this is algebra. Plus 6. So we end up with a +4 is equal to carbon. So then our oxidation numbers are a +4 for carbon, and then a -6 overall for oxygen, +4, and we still have our -2 charge total. So then let's do another one. Let's try NF3, which is nitrogen tetrafluoride. So then total charge equals 0. And then fluorine is a halogen and it's in a compound. So then fluorine, which is equal to a -1 times 3, because we have 3 of them, gives me -3. And then to set up our thing to solve for n, 0 is equal to -3 plus n plus 3 plus 3, so that n equals +3. And so yeah, that's your review for oxidation numbers. It's not that bad. You just have to remember the rules and see what applies in your compound to those rules, and then figure out the missing piece by just equaling it all to your total charge.